This webcast continues the discussion of quantitative force analysis, and now we're going to look at several examples where some of the forces are not parallel to the coordinate axes. Okay, so our first situation here involves Tarzan, and Tarzan is trying to swing through the jungle, but he gets hung up on a branch by his loincloth, and so he's not moving, he's motionless. Okay, so that's important because when I see that word motionless, that tells me that the net force in this situation is 0, right? Since he is not moving, his velocity is not changing. But let's do a force diagram for Tarzan. And I guess we can start with his weight. So there is a gravitational force on Tarzan that's being exerted by the Earth. And let's see, they haven't given me his mass yet, so I'll just record this. I won't calculate the value of that yet. I see him holding on to a vine, and so this vine is exerting a tension force on Tarzan, and remember, tension force is always along the direction is always along the rope or cable or vine or whatever. And so there's a tension force being exerted on Tarzan by the vine. And since they're giving me this angle, I think I'll just, I'm recognizing already that this force is not parallel to either of my coordinate axes. Therefore, I'm going to need to break it into its components. Here is the x component of that force, and here is the y component of that tension force. And then I'm going to go ahead and label this angle since they gave it to me in the figure. Okay. And let's see, are there any other forces? Oh, well, what about his loincloth right here? You know, that's kind of like a rope or a belt or something like that. I mean, it's a piece of fabric that has caught on a branch. So that's also exerting a tension force. And it looks like that is in the horizontal direction. This is a tension force on Tarzan by the loincloth. Okay. Oh, and up here it says that it's pulling, the loincloth is pulling him horizontally to the right. Okay, so I think we have the forces in our force diagram. We know that the net force is 0 since he's not moving. So it says write an equation for the vertical forces on Tarzan. And since there are only 2 vertical forces, and I know that the sum of those vertical forces must be 0, because overall all the forces have to add to 0, then I can say that the y component of the tension force and the force of gravity must be balancing each other. Those are congruent. And so if I wrote an equation for those forces, it would be, I would add the force that goes in the positive direction, which is up, and I would subtract the force that goes in the negative direction, which is down. Okay? And then it says write an equation for the horizontal forces. Well, again, I know that they have to equal 0 because overall in the whole situation all forces have to add to 0. And again, there are only 2 horizontal forces, and so I'm going to put congruency marks on them. And if I wrote the equation, it would be that the tension force being exerted by the loincloth minus the x component of that other tension force. So that has to equal 0. Okay, now they're giving me Tarzan's mass and want me to calculate his weight. Well, I know that the weight is his mass times the acceleration due to gravity. So 75 kilograms times the 9.8 newtons per kilogram. So he weighs 735 newtons. And then it says, let's determine the tension in the vine. Okay, well, let's see here. I know from the sum of the vertical forces equals 0 that the force of gravity has to equal the y component of the tension force in the vine. And let me go up and look here again at my figure. The y component of this tension force is adjacent or next to this 40-degree angle, and this is a right triangle, right? There's a 90-degree angle here, so it's a right triangle. The y component of the tension force is adjacent to the 40-degree angle, and I know that from basic trigonometry that the cosine of an angle equals the adjacent side divided by the hypotenuse. So I could also say that the force of gravity equals the tension force due to the vine times the cosine of 40 degrees. Okay, so I know everything here except for the tension force in the vine. The tension force due to the vine would equal the force of gravity divided by cosine of 40 degrees. So it would be 735 divided by cosine of 40 degrees. And let's see what that is. It equals 959.47 newtons. Okay, so I'm going to go put these on my diagram. This is 735 newtons, and this is 959.47 newtons. Okay, now they want us to find the tension in the loincloth. Well, when I look up here at part C, where I found the sum of the forces in the horizontal direction equals 0, I can say that the tension force in the loincloth must equal the x component of the vine tension force. And that x component of the vine tension force is on the side opposite of that 40-degree angle. So I know that the opposite over the hypotenuse in a right triangle equals the sine of an angle. So therefore, this would equal the tension force in the vine times the sine of 40 degrees, which would equal that 9. I know the tension force in the vine now. We just found that, times sine of 40 degrees. Let's see what that is. So that must be 616.74 newtons. Okay, let's go do another example here. This time I'm going to do an example where we have a situation with something going up a ramp. So here we've got a child pulling a wagon up a hill. The direction of motion is up the hill. So I'm going to tilt my coordinate axes so that the x-axis is parallel to that direction of motion. Remember, I always want one of my axes to be parallel to the direction of motion. Okay, so let's do a diagram for this wagon. It says that the child, and they're giving me the mass of the child, but I'm just doing a force diagram for the wagon, is pulling the wagon up a hill at a constant speed of 0.6 meters per second. So I'm not sure that I care about the amount of the speed, right? But just by saying it's a constant speed in a constant direction up the hill, I know that in this situation the net force is going to be 0 because the velocity of the wagon is not changing. Constant speed and a constant direction means velocity is not changing. Okay. So don't get confused by them giving me the amount of the velocity. That's not what's important. What's important is that it's constant. Okay. Let's see. They've given me the mass of the wagon. It's 12 kilograms, and so I could calculate the weight of the wagon, which is the force of gravity on the wagon by the Earth. And that's going to be the 12 kilograms times the 9.8 newtons per kilogram. So that's 117.6 newtons. Let's see, it says the wagon exerts 60 newtons of force on the child. So this is the applied force on the child by the wagon. But it must also be true that there's a third law pair, which is the applied force on the wagon by the child. So that should also have a magnitude of 60 newtons. Let's see, the child is pulling the wagon up the hill, so the wagon is pulling the child down the hill. Okay, so here is the applied force on the wagon by the child, and that equals 60 newtons. Are there any other forces here? Well, the wagon's not falling through the hill, right? It's being supported on the hill. So there is a normal force perpendicular to where the wheels are pressed into the hill. So there's a normal force being exerted on the wagon by the hill. And I think we have a good set of forces here. The force of gravity is at an angle. It is not parallel to either of my coordinate axes. And so I need to break it into its components. Here is the y component of the force of gravity, and here is the x component of the force of gravity. In situations like this where your axes are tilted, it's a very good idea, it will really be helpful, to show the angle of inclination, if you know it. And so I know from the figure that the hill is at an angle of 30 degrees above the horizontal. And I can trace that back into this right triangle. See the right triangle that's made by the force of gravity and its components. Here's the right angle, here where the components meet. And I need to know one of the other angles in this right triangle so that I can quantify, so that I can calculate the amount of the components of gravity. So the force of gravity goes vertically straight into the earth. So this is a right triangle right here where the force of gravity goes into the ground. And so I can just start doing a little bit of tracing of the angles. You know, if this angle is 30, this angle must be 60, right? Because all of the angles of a triangle have to add up to 180, okay? And then my coordinate axes are perpendicular to each other, so if this angle is 60, this angle must be 30, right? Because they have to add up to form a right angle, 90 degrees. Okay, so now I have an angle inside this triangle, and so I can figure out the size of these components. The y component of the force of gravity must be the force of gravity times the cosine of 30 degrees. It's a cosine because this y component is adjacent to that angle. And the x component is on the opposite side of the triangle from that 30-degree angle, so it must be the force of gravity times the sine of 30 degrees. So I'm just going to calculate those real quickly. So I've got 117.6, that's the force of gravity, times the cosine of 30 degrees. Tells me that the y component is equal to 101.845 newtons, and the x component, which is the 117.6 times the sine of 30 degrees, is 58.8 newtons. Okay. So let's see here. Explain how you used Newton's first law to make the force diagram quantitative. So Newton's first law tells me that when velocity is constant, the net force is 0. Okay, and so we can say here that the normal force must equal the y component of the force of gravity, because the sum of the forces in the vertical direction must equal 0, and that means that the normal force equals FGY. And so I can go ahead and fill that in. And I can also say that the sum of the forces in the horizontal direction equals 0. And so that must mean that the applied force equals the x component of gravity. And I know that they're slightly off here. I'm just noticing this one rounds to 60. There must be a problem in the way I have specified the problem, but those would be equal. What about Newton's third law? So Newton's third law says that all forces are created as pairs. The pair of forces are equal in magnitude but opposite in direction. And that's how we knew that the applied force on the wagon by the child must equal the applied force on the child by the wagon. It's just that it was in the opposite direction. Let's do one more problem here. This is a sign that's hanging outside a physics classroom. It's supported by a cable at an angle of 30 degrees above horizontal by a rigid bar. So this bar is rigid, and it's giving us the mass of the sign and asks us to determine the tension force in this cable here. Okay, so let's do a force diagram for this sign. So the sign has a weight, and I'm able to calculate that amount because they gave me the mass. And so it has a weight of 78. I calculated that wrong. Of 764.4 newtons. And because it's being supported by this rigid bar, the bar is pushing the sign to the right. So there is an applied force on the sign by the bar. I don't know what that is yet. Okay, and also there's a cable, and the cable is pointing in this direction, so that's the direction of the tension force on the sign by the cable. And I can see that that tension force is not parallel to either of my coordinate axes, so I need to break it into its components. Here is the x component of the tension force, and here is the y component of the tension force. They've given me all of the angles. I guess I'll work with this 30-degree angle down here. Okay, so they're asking me to figure out, and that's all they've told me. So let's see if I can, I know that the net force is 0 because it's motionless. And so let me look at the vertical direction. I only have two forces, and so those two forces must be congruent to each other. So I know then that the y component of the tension force equals the force of gravity, and I know the force of gravity. So I'm going to be able to work with that. I also know that in the horizontal direction, again, there are only two forces, so I can say that Ftx, the x component of that tension force, equals the applied force. Not sure I'm going to need that because I only need to find the tension force in the cable. Okay, well, let's see here. Is there another way for me to express the y component of that tension force? It's opposite from the 30-degree angle. Opposite over hypotenuse equals the sine of an angle. So this equals that tension force that I'm looking for times the sine of 30 degrees. And I've calculated Fg, that's 764.4. So the tension force must be 764.4 divided by the sine of 30 degrees. Let's see what that is. So that's 1,528.8 newtons.